Greetings and welcome to part 1 of the calculus series. In this video, we'll be introducing the concept of derivatives and delving in deeper into the derivatives of power functions and polynomials. Oh, and who is this? It seems that Professor Calculus will be sitting in to this lecture and he'll be pointing out some gaps in the lesson. Now before we begin, let me just highlight that before we embark on calculus, one needs to have a strong foundation. Just as you need a basic understanding of arithmetic to understand algebra and basic algebra to understand functions, calculus is a branch of mathematics that builds on all that because it deals with the study of change. And specifically, the first chunk on differentiation will be the study of how fast or slow a function is changing. Hence, before starting this series, we need to have a good grasp on the following family of functions that we'll be exploring. So firstly, we need to be able to manipulate and graph power functions as well as polynomial functions, your trigonometric functions and all the standard identities, and lastly, exponential and logarithmic functions. So along the way, if there are any concepts that might be unfamiliar to you, do check out the corresponding video lecture series. The success criteria for today will be for students to understand the geometrical interpretation of derivatives, to appreciate the derivation of the power rule using limits, and lastly, to differentiate power functions as well as polynomial functions. Firstly, differentiation is the name of the process to find a derivative of a function. The action word or the verb is to differentiate. We start with a geometrical interpretation of what a derivative is. So let's say I have the simplest of quadratic equations, y equals to x squared. At this blue point here, 2, 4, I can draw this purple tangent to the curve. A derivative is basically a gradient function, some general method that tells me the gradient at any point of this curve. So specifically, at this blue point, the gradient would be the gradient of that purple tangent. So before we go to a general case, let's tackle this specific case. How can I find the exact gradient of this purple tangent? Well, first, I can take another point on the curve. Let's take this green point at 4, 16. So we're going to do some estimation. Let's construct this red line known as the secant that passes through 2 points on this blue curve. We can find the gradient of this red secant using the formula y2 minus y1 over x2 minus x1. To some of you, you might know it as rise over the run. So that gives us a gradient of 6. Now this is clearly not the answer, but it's not horribly far away from the truth. So how can we get a bit better in terms of our estimation? So how about if we shift the green point closer to the blue point? So now I've shifted it to x equals to 3, and the corresponding y value will be 3 squared or 9. You can see that if I construct a new secant, this red secant will give us a gradient of 5, a much better approximation. And we can keep improving our estimation by ever shifting the green point closer to the blue point. You can see that at x equals to 2.5, the gradient of the red secant is now 4.5. You can see that the gradient of the red secant line is given by the change in y divided by the change in x. I use this triangle or delta symbol to denote a change in y and the change in x. What we want to do is to keep making that change in x smaller and smaller to get better and better approximations of the gradient. Now I can move the point even closer until we have to magnify this space, and we can see that the change in x now is only 0.001, and the corresponding change in y is 0.004001. This gives us a gradient of 4.001. So we're getting very close to the answer. And I can continue to shrink that change in x But what you can notice by now is m just keeps getting closer and closer to the number 4. In fact, there is no number above 4 that I cannot find a change in x that will give me an estimate of the gradient smaller than that number. So what I hope to convince you is that the gradient is the value of the change in y over the change in x, exactly at the point when x vanishes. And the red secant transforms into that purple tangent. We call this the limit. So you can think of the limit in calculus, this limiting value of the change in y over the change in x, as a trick to find the gradient as the change in x approaches 0. And for this specific case, the gradient is exactly 4. So let me animate this one more time, but this time I'm going to sandwich the gradient on both sides. So I've constructed two red secants, one to the left of the point 2, 4 and one to the right of the point 2, 4. So we can see that the gradient at 2, 4, the gradient of the tangent earlier, has to be greater than the secant on the left side and smaller than the gradient of the secant on the right side. So as we get closer and closer and closer to the point 2, 4, you can see that the gradient of the left secant approaches 3.9 recurring, and the gradient on the right side, the right secant, will approach 4.0 recurring. Therefore, we will be able to conclude that the gradient must be sandwiched between the number 4 on both sides. Therefore, the gradient must be 4. Now that we have seen the geometric intuition for a specific case, let's take the general case of y equals to x to the power of n. And we're going to use the concept of limits to derive the derivative of this power function. So this is a little weird because I haven't really touched much on limits, but I promise to cover limits more rigorously in a subsequent video meant for the A-level and AP exam sections. But bear with this explanation for now. Well, I want to find the gradient of this blue point with coordinates x to the power of n. And I'm going to use h to represent my change in x. So my green point is at x plus h, x plus h to the power of n. So now I can compute the gradient of this red secant using the formula change in y over change in x, which gives me x plus h to the power of n minus x to the power of n over h. So using the binomial theorem, we can expand x plus h to the power of n. And this is going to give us a lot of terms. X to the power of n plus n choose 1, x to the power of n minus 1 times h plus n choose 2, and so on and so forth. So a lot of terms. But basically, you'll see that the first term will cancel out nicely with the x to the power of n that we already had to subtract to begin with. Now, let's look at all the remaining terms in the numerator. Notice that all of them have at least one factor of h. So this is going to cancel out nicely with the h in the denominator. Now we can simplify this. N choose 1 is just n choose 2 is n times n minus 1 over 2. So we'll just simplify all that. Now, let's go back to the diagram for a short while. If we want to find the gradient, we need to make our h as small as possible. So to find our derivative, the dy dx, we are taking the limiting case. So what happens to this function as h tends to 0? Very simply, all these terms, the second term all the way, they are all going to tend to 0. They'll all vanish except for the first term, and that will be our derivative. Oh, hi, Professor Calculus. Did you spot a problem? I see what you're looking at. Maybe we can discuss this after class. Now let's extend this by multiplying an a to the power function. You'll see that this a doesn't really matter because I can factorize the a out before taking the limit. This gives us the formula known as the power rule. Now we can rewrite this. We can say that the derivative, the d by dx of the power function ax to the power n, is given by the formula anx to the power n minus 1. So basically what we do is we multiply by the degree n and we'll subtract 1 from the degree to give us a power of n minus 1. So linking it back to the power graph, the gradient of the tangent at any given point will be given by the formula anx to the power of n minus 1. So let's try to relate this to something a little bit more concrete. Say I have a cube of length x. The volume will be x cubed, and I try to change its size by varying the length x by infinitesimally small change in that x. Can you see that the change in volume is just created by adding 3 areas of x squared to this cube? So 1 here, 1 here, and 1 here. That is why the change in volume is 3x squared, and that fits the formula that we have just derived. Let's move on to some examples. Differentiate the following expressions. Pause the video here and give this question a good try. So let's go through the answer by applying the power rule for derivatives. So in part A, we write d by dx of the expression half x to the power of 4 to show that we are differentiating the expression. Nothing happens to the coefficient half. We bring the exponent 4 down, and we'll subtract 1 from the exponent to get x to the power of 3. So when we simplify this, we'll get 2x cubed. In part B, we'll take the derivative of negative 5 x to the power of negative 2. So nothing happens to the coefficient negative 5. We bring the exponent negative 2 down, and we'll subtract 1 from the exponent to get a power of negative 3. So when we simplify this, we'll get 10x to the power of negative 3. We can rewrite this in positive index notation. This will give us 10 over x cubed. In part C, we take the derivative. Again, nothing happens to the coefficient pi. We'll bring the exponent down, so we'll times 1/3 and subtract 1 from the exponent. Simplifying, we'll get pi over 3 times x to the power of negative 2 over 3. Again, we can rewrite this in positive index notation. We can also divide the rules for differentiation into 2 broad categories: those that apply to specific types of functions and those that are general rules that apply to all functions. Specifically, we have covered the power rule that applies specifically to power functions and polynomial functions. For general rules, we have seen how that when we multiply a constant a to some function u, it is the same as multiplying a to the derivative of u. Now we're going to prove one more general rule, which is related to the addition and subtraction of 2 functions u and v. So I'm only going to prove this for addition. Feel free to repeat this again for subtraction. So let's look at the definition of derivatives using limits. I'm taking the function for x plus h, I subtract the function for x, and I divide it over h, and I want h to tend to 0. So what I do is I rearrange the numerator, and I'm going to split this into 2 separate fractions. And each fraction is a limit that gives us du dx and dv dx. This tells us that the derivative of the sum of 2 functions is the sum of the respective derivatives of the individual functions. So graphically, what does this mean? So if I take this blue function and I add it to this red function, and I get the sum, this green function, the gradient at any point of the green function will be equal to the gradient of the blue function plus the gradient of the red function as well. So using the rules that we've covered so far, try example 2. Differentiate these 2 following functions f and g. Pause the video here and give this question a good try. Now, before we differentiate, it's always nice to convert everything to its exponents form. So square root of x gives us x to the power of half, and for the constant term 7, we can add an x to the power of 0 beside it. Instead of writing df dx, I'm going to use the Lagrange notation instead, so I'll write f prime x to represent the derivative. Now this will give us this following expression. So basically I've multiplied by the exponent and subtracted each exponent by 1. The final answer will be 10x minus 3 over 2 root x. Now I just want to focus on what happened to the 7. Notice that the 7 when differentiated gives us nothing. Why is that so? Because adding a 7 is just adding a horizontal line, and a horizontal line has a gradient of 0. So that should also give you a visual understanding of why it disappears. For part B, we have a fraction consisting of two polynomial functions. The trick here is to just divide all the terms in the numerator by the denominator of x squared. So that will give us 3x squared minus 6 plus 5 over x squared. So the derivative g prime x would just be 6x minus 10 over x cubed. Once again, because the 6 is a horizontal line, it has 0 gradient, so that term disappears completely. So in example 3, I have a curve y equals to x cubed minus 2x squared minus 4x plus 8. So this is a cubic equation. I want the coordinates of the points on the curve where the gradient is 3. So pause the video here and give this question a good try. So graphically, the cubic equation looks like this, and our aim is to find the 2 points on this green curve where the tangents have a gradient of 3. So I take the cubic equation and I differentiate it to find the derivative. So the dy dx, or the gradient function, is this quadratic equation. And I set the gradient to be 3. So now I just have to solve this quadratic equation. I bring the 3 over and then I factorize it. This tells me that x is either equals to -1 or 7 over 3. So I can substitute the values back into the original cubic equation, and this will tell me the y values for the respective x. So by doing so, I get the point -1, 9, as well as 7 over 3, 13 over 27. So this will be my final answer. So do also check out the info section below, where I'll give you the link to my website, and you can also test yourself by generating some extra practice questions and self-check your own answers with various levels of difficulties for this topic. So before we conclude, let's return to the success criteria that we set out at the start of the lesson. So are you now better able to understand the geometrical interpretation of derivatives, appreciate the derivation of the power rule using limits, and most importantly, are you able to differentiate various power functions as well as polynomial functions? So if any queries on any of these success criteria, do post them in the comment section below. So we've come to the end of part 1 on the derivatives of power functions as well as polynomial functions. In the next video, we'll look at the chain rule. Thank you and have a great day off. Oh, hi, Professor Calculus. You want to raise an issue? Sure, let's look at your problem. Professor Calculus is not convinced why the binomial theorem applies here. Because for power functions, n can be any real number. But doesn't the binomial theorem that we learn of only work for positive integers? Well, we usually don't bother explaining it for general power functions, but I'll make an exception here. In actual fact, the binomial theorem can be generalized to also include negative exponents, fractional powers, even all real numbers. So let me explain this briefly. So in the year 1665, before Newton invented calculus, he actually generalized the binomial theorem so that n can be any real number. So let me go through the idea of the proof by just first going through the computation of combinatorial functions for decimals. So this is the general formula for n choose r. If we plug in n equals to 5 and r equals to 2, we get 5 choose 2, which computes to be 10. So what happens when n is 0.5? So we have 0.5 choose 2. So we need to first compute 0.5 factorial. So we can just use this little trick where we take 0.5 Then we multiply by n minus 1, which is negative 0.5. Then keep subtracting 1 and multiplying it, so times negative 1.5 times negative 2.5, and so on and so forth. So in the denominator, we have r factorial, which is just 2 factorial, nothing happens there. And then we have n minus r factorial. So n minus r gives us negative 1.5, 0.5 minus 2. So again, we do the same trick. So after we times negative 1.5, we times negative 2.5, so on and so forth. Notice that everything after the third term cancels away. So all we're left with is 0.5 times negative 0.5 divided by 2, and that gives us negative 1 over 8. Notice that this is also the exact same result if we were to use the other formula of n times n minus 1 divided by 2. So both methods will give us the same value. So let's try to make sense of that strange result that 0.5 choose 2 gives us negative 1 over 8. So we'll look at the expansion of 1 plus x to the power of half. So first we have to assume that such an expansion is possible, and that will give us a power series a0 plus a1x plus a2x squared, so on and so forth. And we need to evaluate each of these coefficients. a0 is the easiest because we can just sub x equals to 0 on both sides. That tells us that a0 is equals to 1. So how do we find a1? Oh, Professor Calculus, you think you can use this advanced method known as the Maclaurin series? Well, for more advanced students, you might be familiar with it, but you can't use that because that requires you to differentiate on both sides, and that would be like using a to prove b, b to prove a. That's a tautology, so go away for now. What we should do is we should square both sides instead. The left-hand side will give us 1 plus x, and the right-hand side, well, that's going to be a pain to expand, but we'll just slowly do it. And once you do it, you can compare the coefficients on both sides. You'll see that a1 equals to half, a2 equals to negative 1 over 8. Now, the two things I want you to notice here. Notice that a1 equals to half is exactly the power that we wanted to expand for. The other thing is that a2 equals to negative 1 over 8 is 0.5 choose 2. So this is going to verify that the binomial theorem does indeed work for power half. And we can generalize this method for any positive fraction m over n. So we can just raise both sides by the power n, expand the left-hand side, expand the right-hand side, compare the coefficients for the x terms, and you'll see that the coefficient a1 will be m over n. And that's exactly the power that we started off with. You'll also be able to see that for any coefficient for the nth term an, it will be m over n choose n. So this works out for the general expansion of binomials for any positive fraction. Let me also just show you that it works for negative powers. So let's say negative 1 choose 2. Well, n factorial in this case will be negative 1 times negative 2 times negative 3, so on and so forth. The denominator will have 2 factorial, and n minus r would be negative 3. So we'll take negative 3 factorial, so we'll just multiply by negative 4, negative 5, so on. Cancel all the terms, and you'll see that this gives us 1. So how does that strange result of negative 1 choose 2 equals to 1 compare with the power series expansion for 1 plus x to the power of negative 1? So assuming that the power series does indeed exist, again a0 has to be 1. We sub in x equals to 0 on both sides. And now the trick here is I'm going to multiply 1 plus x on both sides. So the left-hand side will now be 1, and the right-hand side will be 1 plus x multiplied by that infinite power series. So we can expand that, and this will be quite easy to compare. 1 is equals to 1, so the rest of the coefficients have to be 0. So we can show that a1 equals to negative 1, then that's equals to the power that verifies that the coefficient will always be the power. Then a2 we can show that's equals to 1, and that also checks out with the negative 1 choose 2. I hope this convinces Professor Calculus that the binomial expansion can work for any value of n, and that is why that the proof for calculus works not just for integer powers but for any real number. I confess that there are still gaps in this explanation, but I'll leave your real analysis teacher to cover those gaps. Now we will really stop here. Thank you for your kind attention watching through the entire post-credit scene, and see you in the next lecture.